Without warning, a solid iron boiler gives way, instantly expanding its pressurized water into steam and leveling the factory around it. In the early 19th century, catastrophic blasts like this were a frequent reality. In 1838, all 4 boilers on the steamboat Moselle burst simultaneously. In 1854, a commercial boiler explosion completely demolished a factory in Rochdale. The physical toll of these failures was horrific. 300-pound iron plates were hurled hundreds of yards through the air, shredding brick, timber, and flesh, while the rapidly expanding steam caused massive casualties. Before the development of modern metallurgy and mechanical regulation, the quest to harness centralized heat was a deadly gamble. Engineers were turning basements into ticking time bombs. To understand why people accepted these risks, look at the alternative. British society relied entirely on open coal fireplaces, which were highly polluting and lost most of their thermal energy straight up the chimney. Try heating a space like the circular British Museum reading room with a few scattered grates. The thermal energy simply cannot overcome the drafts and sheer volume of these new industrial age structures. Engineers first scaled up by moving the fire directly into the room. Charles Portway developed the cast iron tortoise stove, utilizing a slow, solid fuel combustion that radiated heat locally. Goldsworthy-Gurney expanded on this with a massive stove featuring 24 cast iron fins. It rested in a trough of water to humidify the dry air while it distributed heat, allowing it to warm massive interiors like St. Paul's and Chester cathedrals. But a stove can only push convective air so far. To move heat across vast distances without choking the occupants on dry, dusty drafts, engineers realized they had to seal the thermal energy inside pipes using highly pressurized water. In 1831, an inventor named Angier March Perkins discarded the standard boiler entirely. He designed a continuous, hermetically sealed loop of water. A portion of the iron pipe was coiled directly into a blazing brick furnace. The sealed water reached 200 degrees Celsius at immense pressure. The loop held together because Perkins' custom-threaded joints drew the pipe ends together seamlessly, withstanding the internal force. However, stringing uninsulated iron pipes through the wooden framing of grand estates carried severe consequences. Direct contact ignited structural fires, and manual control meant temperature spikes often triggered explosive pipe ruptures. By 1841, fire insurance companies explicitly refused to cover buildings using the high-pressure apparatus. The heating industry had to find a way to distribute heat without turning the pipes into a liability. They turned to low-pressure gravity systems. These networks operated entirely passively, with zero mechanical circulating pumps. In a thermosiphon, heated water decreases in density. This buoyant, hot water naturally rises up a vertical express riser to an open attic expansion tank. Flowing through radiators, it transfers heat, cools, becomes denser, and is pulled back down by gravity to repeat the cycle. Because the driving pressure generated by this temperature difference was so small, the water moved at a crawl. Engineers used massive cast iron pipes, sometimes 4 inches across, just to minimize internal friction. To speed up the flow without bursting the open attic tank, companies like Honeywell developed devices like the heat generator. It used a heavy column of liquid mercury to safely separate the open tank from the boiler, allowing the system to build up to 10 pounds of pressure and circulate the water much faster. While the thermosiphon safely eliminated the extreme physics of the Perkins loop, it still left the physical equipment at the mercy of the most volatile variable, the humans shoveling the coal. If a factory was cold, operators routinely stacked heavy iron weights onto safety valve levers, physically pinning them down to force more heat. To prevent catastrophic meltdowns from low water levels, engineers relied on Richard Trevithick's fusible plug. It was a brass cylinder with a pure tin core, screwed into the firebox. If the water dropped, the core melted at 232 degrees Celsius, venting a loud blast of steam to suppress the fire. This metallurgical analysis reveals that just 0.3% zinc impurities created an interlocking network of zinc oxide. This infusible crust had such a high melting point that the plug stayed sealed even after the tin melted, trapping pressure until the boiler explosively failed. Engineers adopted tamper-proof mechanics, like the Ramsbottom safety valve. Utilizing internal springs, it snapped open automatically and was nearly impossible for operators to manually override. The identification of these microscopic material flaws and the introduction of mechanical overrides established the predictable technical standards required for safe operation in public spaces. Decades of factory explosions and steamboat disasters eventually broke public tolerance. In 1855, following the Rochdale boiler blast, mill owners and engineers formed the voluntary Manchester Steam Users Association to track and prevent failures. These voluntary guidelines laid the groundwork for mandatory government legislation. Following further tragedies, the industry published the 1915 ASME Boiler and Pressure Vessel Code, setting strict universal requirements for fabrication and testing. The documentation of these failures, from the 1882 Boiler Explosions Act to the 1915 ASME Code, formed the structural foundation for the pressurized vessel regulations that continue to govern modern heating infrastructure. Eventually, engineers mastered pressurized water so thoroughly that they could safely bury the piping beneath the floorboards of grand historic architecture, providing invisible warmth. Bath Abbey is a prime example. For over a century, this space was kept warm by a traditional network of coal-fired trench heating systems. Today, the Abbey utilizes geothermal heat pumps to reclaim waste thermal energy directly from the Great Drain of the nearby Roman baths. By safely reclaiming energy from natural sources, modern engineering has moved past the volatile chemistry of coal and high-pressure steam, relying instead on the same physics of fluid dynamics that Victorian engineers first attempted to harness.